Welcome to this video on nuclear chemistry notes. So we are trying to understand the changes that occur in the nucleus of atoms specifically. So in class today we were talking specifically about parts 1 and 2 where we were reviewing atomic structure, seeing how it connected to the periodic table, and starting to talk about isotopes. Now this video is particularly on parts 3 and 4 where we're going over nuclear change equations or how to model nuclear changes and a little bit on half-life as well. If you're interested in reviewing parts 1 and 2, you can watch the additional video that's posted with this assignment on NEO. So nuclear change equations. We want to be able to model nuclear decay without having to draw out sample atoms, especially as we're talking about really large nuclei. So we need a way to do that without having to draw them. Now, nuclear change equations are modeling what's called radiation. Radiation is when particles or energy are emitted or given off by an unstable isotope. So what's an unstable isotope? Well, we can see here at the bottom, an unstable isotope is something that's unstable because an atom's ratio of protons and neutrons is off. So whatever is happening in the nucleus causes some instability. And in order to try to become more stable, the atom is going to emit these particles or energy. And you'll notice that particles and energy are not spontaneously emitted from regular or stable atoms. So regular atoms don't do this. This is specifically for radioactive atoms. There's 3 types of radioactive decay: alpha, beta, and gamma. Alpha, if you're drawing it, is kind of like part of a fish that you're drawing. Beta is just a capital B with a tail. And gamma is a Y with a bit of a curvy neck. And the difference between these 3 types is just what is being emitted. What is this unstable nucleus throwing off? And we can categorize it as either alpha, beta, or gamma decay. So we're going to use nuclear change equations to model this, to model alpha, beta, and gamma. And so I wanted to just show you what that looks like in an equation. So you can see in both of our examples, this first one, we have uranium-235 over here on, let me highlight it for you. So we have uranium-235, and then it's undergoing radioactive decay, meaning it's emitting an alpha particle, and it's becoming a new isotope. So we're going to use these equations, basically these equations. All we're going to do is we'll have some sort of parent nuclide, some sort of radioisotope that we're starting with, and we're just going to model, okay, it's decaying into some particle plus some new isotope. So we'll see more of these as we get through, once we have more information on these beta particles, alpha particles, gamma waves. So real briefly, why is radiation dangerous? We hear that a lot, and we're going to talk a lot more about this later, but just so you have some context going in, is that all these types of radiations, whether it's alpha, beta, or gamma, are high energy, teeny tiny particles or waves, and what happens is they cause damage to the DNA of our cells, and this can most often lead to cancer. There's certainly other issues it can lead to as well, and not all types of radiation harm us equally. We'll notice there's differences in alpha and beta and gamma radiation. So at this point, pause the video and set up your table in your notebook if you haven't already. Welcome back. So first we're going to fill out the top row. We're going to say, what is it for alpha, beta, and gamma? So an alpha particle is just that, it's a particle. And what it is a helium nucleus. Notice this word nucleus, not atom. And that's because there's no electrons. It's just the 2 neutrons and 2 protons that are thrown off. So we can tell because there's a mass of 4 with 2 protons. That's how we know it's helium, because everything with 2 protons is helium. So when something undergoes alpha decay, it is throwing off a helium nucleus. For beta decay, we're throwing off another particle, but this one is smaller. This one's just an electron. You'll notice we don't have any chemical symbol here because a -1, ooh, look at that. That's not an atomic number. That's telling us the charge, and there's no mass. Finally, gamma radiation is not a particle at all. It's simply a high-frequency electromagnetic wave. And you might recognize this word gamma from physics when you learned about electromagnetic waves. We know that gamma waves have the highest frequency of any waves. So now you're filling in the alpha column of that table. Our alpha radiation is when our parent radioisotope throws off a helium nucleus. So its mass changes by 4 AMU. It loses 2 neutrons and 2 protons. These alpha particles can travel 3 to 5 centimeters in the air. That's about 1 to 2 inches. It can be stopped simply by a piece of paper or skin. It's quite easy to stop alpha particles. The example that we have here is americium-241 undergoing alpha decay, losing 4 AMU, including its 2 protons, to become our new isotope of neptunium-237. And I found out that that was neptunium because I knew the mass was 237, so I looked up what my atomic number 93 was on my periodic table, and I found neptunium. Our beta decay, so in this case we are throwing off an electron from our radioisotope. The atom's mass doesn't change at all. We're not throwing off any mass. These can travel further because they're much smaller. They can travel 2 to 3 meters, that's about 6.5 to 10 feet. These can be stopped by a thin layer of glass or metal, 3 meters of air, or 2 inches of water. And notice for this one, the atomic mass is increasing by 1. These are weird for beta decay. So we're not losing mass, but because of this charge, what happens in beta decay is, for this case, cobalt-60 emits an electron, and what happens is it also converts a neutron into a proton. So this nickel has one higher atomic mass. You'll notice it went from 27 to 28, but the same mass. So our mass has stayed the same, but we've converted a neutron into a proton to increase that atomic number, and that makes the isotope more stable. Beta radioisotopes are the kinds most commonly used in cancer therapies. Finally, we have our gamma radiation. We have a high-frequency electromagnetic wave, so we're not changing the mass at all. Gamma waves can travel galaxies incredibly, incredibly far. It can be stopped by 4.2 meters of water. That's a lot of water. That's probably around 40 feet. 2 meters of concrete, very, very, very thick concrete, about 6.5 feet of concrete, or just 0.4 meters of lead. That's still over a foot. It's a lot of lead that's required to stop these very high-frequency gamma waves. And you can tell that our equation, our isotope, doesn't change at all. We're just modeling that there's energy being released from it. So it's a super high-energy gamma wave being emitted, in this case from argon-40. This is just a visual. You'll notice that alpha and beta are our 2 particles. So we can see that an alpha particle up here with my 2 protons and my 2 neutrons is larger than my tiny electron particle for beta. That's why beta waves can travel further. And then finally, gamma is just a wavelength of energy. There's no particles at all. Let's talk about half-life. So half-life is important because it answers how much radiation is actually being given off a sample. The half-life of a radioisotope is the time it takes for half of the existing radioisotopes to decay into a different isotope. So basically it tells us, is it decaying really quickly? It's releasing a lot of radiation really quickly with a short half-life, so it's decreasing really rapidly. Or is it decaying more slowly over time and it's releasing its radiation in more slow doses over a longer period of time? And we abbreviate it, as you can see written down at the bottom, as T with a subscript of 1/2. That's our abbreviation for half-life. So radioisotopes with really long half-lives, things like thousands of years, uranium is a good example of this, continue to emit harmful ionizing radiation for really long periods of time. So they release low levels of radiation over very long periods of time. Radioisotopes with short half-lives, so something like seconds, minutes, hours, or days, these are really scary because they emit a lot of radiation very quickly. But after some time has passed, the sample has decayed so much, it's not releasing very much radiation at all. So they're very different. Something with a very long half-life, we would not want to be around it for very long because it's continuing to emit low levels of radiation. Something with a very short half-life, we wouldn't want to be near at all while it's decaying, but after it's had a chance to decay for seconds, minutes, hours, days, then it wouldn't be emitting very much radiation. So the only visual I want us to go over together, you can view the rest on your own, is this first one. So this is just a nice summary, and I do recommend if you have a printer to print this out. This is also already in the chemistry packet if you've picked it up, but it shows us a really good example of what these are actually looking like. So you can see it's just alpha, beta, and gamma. We have our notation written out here in a sample equation, but I really like these models. I think these are very helpful to see what's actually happening with those particles being emitted or the energy being emitted. So I recommend that you have this as some reference because it's nice to visualize what those nuclear change equations are actually looking like for the isotope. I hope that was helpful. Feel free to watch the first part if you want a little review from class. Otherwise, we'll get working on our practice sheet when I see you all tomorrow.